Introduction to Round Trip Time. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this presentation, we are going to explore round trip time, commonly known as RTT, and understand its profound implications on network performance. RTT is one of the most fundamental metrics in networking, yet it is often overlooked or misunderstood by many network engineers and system administrators. Round trip time measures the total time it takes for a signal or packet to travel from a source to a destination and back again. Think of it like sending a letter and waiting for a reply. The time from when you drop the letter in the mailbox until you receive a response is analogous to RTT in networking terms. Understanding RTT is critical because it directly impacts user experience, application performance, and the overall efficiency of your network infrastructure. When users complain about slow applications or laggy connections, RTT is often a significant contributing factor. Let me walk you through the diagram that illustrates the basic concept of round trip time. We have a client on one side and a server on the other. The client initiates communication by sending a request to the server. This request travels across the network, traversing various network devices, cables, and potentially the internet. Once the server receives this request, it processes it and sends back a response to the client. The total time from when the client sends the request until it receives the response is the round trip time. The diagram shows this bidirectional communication with arrows indicating the direction of data flow. The request arrow flows from client to server, representing the outbound journey. The response arrow flows from server back to client, representing the return journey. The combined time of both journeys, plus any processing time at the server, constitutes the complete RTT measurement. Throughout this presentation, we will examine the components that make up RTT, how it affects TCP performance, the relationship between RTT and bandwidth, and strategies to minimize its impact on your network applications. Measuring RTT with network tools. Now let us explore how to actually measure round-trip time in real-world scenarios. Network engineers have several tools at their disposal, with ping being the most fundamental and widely used utility for round-trip time measurement. The ping command sends Internet Control Message Protocol, or ICMP, echo request packets to a target host and waits for echo reply packets. By measuring the time between sending the request and receiving the reply, ping calculates the RTT for each packet exchange. Let me walk through the command example shown on the slide. The command begins with ping, which is the utility we are invoking. The flag -C followed by the number 4 specifies the count parameter, telling ping to send exactly 4 ICMP echo request packets before stopping. Without this parameter, ping would continue indefinitely until manually interrupted. The target 8.8.8.8 is Google's public DNS server, which is commonly used for network testing because it is highly available and geographically distributed. The output shows several important pieces of information. Each line beginning with 64 bytes from represents a successful echo reply. The number 64 indicates the size of the reply packet in bytes. The ICMP_seek parameter shows the sequence number of each packet, incrementing from 1 to 4, which helps identify packet loss or reordering. The TTL value of 117 represents the time to live remaining after the packet traversed the network path, giving you an indication of how many hops the packet traveled. The most important value for our discussion is time, shown in milliseconds. The 4 responses show times of 12.3, 11.8, 12.1, and 11.9 milliseconds. These values represent the individual RTT measurements for each packet exchange. The summary statistics at the bottom provide aggregate information. The line showing 4 packets transmitted and 4 received with 0% packet loss confirms that all packets successfully completed the round trip. The final line shows the RTT statistics. Minimum of 11.8 milliseconds, average of 12.025 milliseconds, maximum of 12.3 milliseconds, and a mean deviation of 0.194 milliseconds. The mean deviation, sometimes called MDEV, indicates the consistency of RTT measurements. A low MDEV value suggests stable network conditions, while high variability might indicate congestion or routing instability. When interpreting ping results, remember that Internet Control Message Protocol packets may be treated differently by network devices compared to regular Transmission Control Protocol or User Datagram Protocol traffic. Some routers deprioritize Internet Control Message Protocol processing, and some firewalls may rate limit or block Internet Control Message Protocol entirely. Therefore, while ping provides valuable baseline measurements, application-specific round-trip time may differ from ping results. The bandwidth delay product. The bandwidth delay product, commonly abbreviated as BDP, is a critical concept that quantifies the amount of data that can be in transit on a network connection at any given moment. Understanding BDP is essential for properly configuring TCP parameters and achieving optimal network performance. BDP is calculated by multiplying the available bandwidth by the round-trip time. The result represents the volume of data that can be in flight, meaning data that has been sent but not yet acknowledged. This value is sometimes referred to as the pipe capacity because it represents how much data can fill the virtual pipe between sender and receiver. Let us work through a concrete example. Consider a network link with 100 megabits per second of bandwidth and an RTT of 50 milliseconds. To calculate BDP, we multiply 100 megabits per second by 0.050 seconds, which equals 5 megabits, or 625 kilobytes. This means that at any moment, up to 625 kilobytes of data can be traveling through this connection. The significance of BDP becomes clear when we consider TCP window sizing. For TCP to fully utilize the available bandwidth, the window size must be at least equal to the BDP. If the window size is smaller than the BDP, the sender will be forced to wait for acknowledgements before the pipe is full, resulting in underutilization of the available bandwidth. This condition is sometimes called having an undersized window. Let me explain the diagram that illustrates the BDP concept visually. The diagram represents a network connection as a pipe flowing from the sender through the network pipe to the receiver. The BDP data in flight component sits within the network pipe, representing all the data currently traveling through the network that has been sent but not yet acknowledged. The arrows show the direction of data flow. The sender pushes data into the pipe. This data travels through the network as BDP data in flight, and eventually reaches the receiver. The receiver then sends acknowledgements back through the ACK return path to the sender, confirming receipt of the data. The time for data to travel to the receiver and acknowledgements to return constitutes the RTT, and the BDP represents the maximum amount of data that can occupy this pipe at any given instant. For high bandwidth, high latency connections, the BDP can be substantial. A 10 gigabits per second link with 100 milliseconds RTT has a BDP of 1 gigabit, or 125 megabytes. Traditional TCP window sizes were limited to 64 kilobytes due to the 16-bit window field in the TCP header, which is woefully inadequate for such connections. This limitation led to the development of TCP window scaling, which we will discuss in a subsequent slide. RTT impact on application performance. Beyond the technical mechanics of TCP, RTT has direct and measurable impacts on the applications that users interact with daily. Understanding these impacts helps network engineers and application developers make informed decisions about architecture, deployment locations, and optimization strategies. Web applications are particularly sensitive to RTT because of the way browsers fetch web pages. A modern web page typically requires dozens or even hundreds of individual resources: HTML documents, CSS style sheets, JavaScript files, images, fonts, and API calls. Each of these resources requires at least one round trip to request and another to receive the response. High RTT multiplies these delays across all resources, resulting in noticeably slower page load times. Consider a web page that requires 50 resources with an RTT of 20 milliseconds. Even with HTTP/HTTPS multiplexing, the cumulative impact of RTT on page load time is significant. Increasing RTT to 200 milliseconds can transform a snappy 2-second page load into a frustrating 10-second experience. Database-driven applications face similar challenges. When an application server queries a remote database, each query incurs the full RTT penalty. An application making 20 sequential database queries with 50 milliseconds RTT adds a full second of latency just from network round trips, regardless of how fast the database processes the queries. Let me explain the diagram that shows the user experience timeline for a web page request. The flow begins with the user, who initiates an interaction by clicking or requesting a resource. This request travels to the browser, which must process the user action and formulate the appropriate HTTP request. The browser then sends the request to the server. This transmission incurs the first half of the ART as the request travels across the network. The server receives the request, processes it by fetching data, executing business logic, and generating the response. Server processing time is separate from ART but adds to the total latency. Once processing completes, the server sends the response back to the browser. This return journey incurs the second half of the RTT. The browser receives the response and must render the content, parsing HTML, applying CSS, executing JavaScript, and painting pixels to the screen. Finally, the user perceives the page load, completing the interaction. The critical insight from this flow is that every round trip in this chain is multiplied by RTT. Initial HTML request, CSS files, JavaScript files, API calls, image requests all compound these delays. This is why edge computing, content delivery networks, and strategic server placement have become essential strategies for delivering responsive user experiences in a globally connected world. Strategies to reduce RTT impact. While we cannot change the speed of light, there are numerous strategies available to minimize the impact of RTT on network and application performance. These techniques range from infrastructure choices to protocol optimizations to application architecture decisions. Content delivery networks, or CDNs, are perhaps the most widely deployed solution for reducing RTT impact. CDNs distribute content to edge servers located in close geographic proximity to end users. When a user requests content, they are served from a nearby edge server rather than a distant origin server, dramatically reducing RTT for cached content. Edge computing extends the CDN concept by moving not just content but computation closer to users. By processing requests at edge locations, applications can reduce the number of round trips to central data centers, particularly for API calls and dynamic content generation. Protocol optimizations can also reduce RTT impact. HTTP/2 and HTTP/3 enable multiplexing, allowing multiple requests and responses to share a single connection without head-of-line blocking. This means that one slow response does not delay others, improving overall page load times even when individual RTT values remain constant. TCP optimizations, including larger initial congestion windows, TCP fast open, and aggressive window scaling, help connections reach optimal throughput more quickly. These optimizations reduce the number of round trips required during connection establishment and slow start phases. Let me explain the diagram that illustrates how CDN edge servers reduce RTT for users. The flow begins with the user, who needs to access content from a website or application. Rather than sending requests directly to a distant origin, the user connects to a CDN edge server that is geographically nearby. The arrow from user to CDN edge server is labeled low RTT, indicating the minimal latency due to short physical distance. The CDN edge server maintains a cache of frequently accessed content, When the user's request can be served from this cache, the response is immediate, requiring only the low or TT round trip to the edge. For content not in the cache, the CDN Edge server connects to the origin server on behalf of the user. This connection from CDN Edge server to origin server is labeled high RTT because the origin may be geographically distant. However, this high RTT penalty is only paid once, when the content is first fetched and cached. Subsequent requests from the same or other nearby users are served directly from the CDN Edge server cache, experiencing only the low RTT connection. The origin server sends the full content to the CDN Edge server, which caches it and forwards the cached content back to the user. Application-level optimizations also play a crucial role, reducing the number of required round trips through techniques like request batching, persistent connections, connection pooling, and speculative prefetching can dramatically improve perceived performance even when underlying RTT values are high. Monitoring and measuring RTT. Effective RTT management requires continuous monitoring and measurement. Without visibility into actual RTT values across your network, you cannot identify problems, track trends, or verify the effectiveness of optimization efforts. Passive monitoring captures RTT measurements from production traffic without injecting test packets. By examining TCP timestamps and acknowledgement patterns, network monitoring tools can calculate RTT for actual application flows. This approach provides realistic measurements that reflect real user experience but requires access to packet captures or flow data. Active monitoring uses synthetic probes to measure RTT between specific endpoints. Tools like ping, traceroute, and specialized monitoring platforms send test packets at regular intervals and record response times. Active monitoring provides consistent baseline measurements and can detect issues before they impact users, but test traffic may follow different paths or receive different treatment than application traffic. Application Performance Monitoring, or APM. Tools measure RTT at the application layer, capturing the full round-trip time including all protocol overhead and processing delays. These measurements most accurately reflect user experience but require instrumentation of applications. Let me walk through the code example that demonstrates basic RTT monitoring using a shell script. The script begins with the shebang line specifying bash as the interpreter, followed by two variable definitions. The target variable is set to 8.8.8.8, which is Google's public DNS server and serves as our monitoring endpoint. The interval variable is set to 60, indicating that we want to measure RTT every 60 seconds. The script enters an infinite loop with the while true construct. Inside this loop, the timestamp variable captures the current date and time in ISO 8601 format using the +sign format specifier with %signs around the various date and time components. The core measurement is performed by the ping command. The -C1 flag specifies sending exactly one packet, keeping each measurement quick and lightweight. The -W5 flag sets a timeout of 5 seconds, ensuring the script does not hang indefinitely if the target is unreachable. The output is piped through grep to extract only the line containing time equals, which contains the RTT measurement. The awk command with -F as the field separator extracts just the numeric RTT value in milliseconds by printing the second field after splitting on the equals sign, and then removing the trailing units indicator. Finally, the echo command outputs the timestamp and RTT values separated by a comma, creating a simple CSV format suitable for logging or analysis. The double greater than operator appends each measurement to a log file named RTT_log.csv, building a historical record of RTT measurements over time. The sleep command pauses execution for the specified interval before the loop repeats, ensuring measurements are taken at regular, predictable intervals. This simple script provides a foundation for RTT monitoring that can be extended with alerting, visualization, and more sophisticated analysis as needed. TCP congestion control and RTT. TCP congestion control algorithms are deeply intertwined with RTT measurements. Understanding this relationship is essential for diagnosing performance issues and tuning network applications for optimal throughput. TCP uses RTT measurements to calculate the retransmission timeout, or RTO, which determines how long a sender waits before concluding that a packet was lost and needs to be retransmitted. The RTO is dynamically calculated based on observed RTT values and their variance. If RTT suddenly increases due to congestion, the RTO adjusts accordingly to avoid premature retransmissions. The congestion window, often abbreviated as CWND, controls how much data TCP can send before receiving acknowledgements. During the slow start phase, the congestion window grows exponentially, doubling with each RTT. A connection with 10 millisecond RTT can grow its window much faster than one with 100 millisecond RTT, simply because more round trips occur per unit of time. After slow start, TCP enters congestion avoidance mode, where the window grows linearly, adding approximately one segment per RTT. Again, low RTT connections can increase their throughput more rapidly than high RTT connections. This behavior explains why two connections with identical bandwidth but different RTT values achieve dramatically different throughput during the initial ramp-up period. Let me walk through the diagram that illustrates how RTT affects the TCP congestion window growth. The flow begins with connection start, representing a new TCP connection being established. From there, the connection enters the slow start phase. During slow start, the congestion window increases exponentially. The diagram shows this relationship where each RTT cycle allows the window to double in size. The connection continues through exponential growth until it reaches the slow start threshold, at which point it transitions to congestion avoidance. In this phase, represented by linear growth, the window increases by approximately one maximum segment size per RTT. The rate of growth is directly tied to how quickly RTT cycles complete. The critical insight shown in the diagram is the annotation indicating that low RTT equals faster window growth. A connection with 20 millisecond RTT experiences 50 round trips per second, while a connection with 200 millisecond RTT experiences only 5 round trips per second. This tenfold difference in RTT cycles translates directly to how quickly each connection can grow its congestion window and reach optimal throughput. Modern congestion control algorithms like BBR, developed by Google, take a different approach by directly measuring bottleneck bandwidth and RTT to optimize sending rate, but even BBR relies heavily on accurate RTT measurements for its calculations. RTT in cloud environments. Cloud computing introduces unique RTT considerations that differ significantly from traditional on-premises networking. Understanding these factors is crucial for architecting performant cloud applications and services. Within a single cloud region, RTT between virtual machines is typically very low, often under 1 millisecond for instances in the same availability zone. However, cross-zone traffic within the same region may add 1 to 2 milliseconds, and cross-region traffic can introduce RTT comparable to traditional internet connections, ranging from 20 milliseconds for nearby regions to over 200 milliseconds for intercontinental communication. Cloud providers offer specialized networking features to optimize RTT. AWS Global Accelerator and Azure Front Door route traffic through the provider's backbone network rather than the public internet, often reducing RTT by avoiding congested internet exchange points. Google Cloud's premium tier networking similarly uses Google's private fiber network for improved latency. Microservices architectures common in cloud environments amplify RTT concerns. A single user request might traverse dozens of internal service calls, each adding its own RTT overhead. If each service call adds 5 milliseconds of network latency, a request touching 20 services accumulates 100 milliseconds of network delay before any processing time is considered. Let me walk through the diagram illustrating RTT paths in a cloud deployment. The flow begins with the user, who initiates a request to the cloud application. This request first reaches the load balancer, which serves as the entry point to the cloud infrastructure. The arrow from user to load balancer represents the external network RTT, which varies based on user location and internet conditions. From the load balancer, traffic flows to the web tier, which handles the initial request processing. The RTT between these components is typically very low, often sub-millisecond, because they reside in the same cloud region. The web tier then communicates with the app tier for business logic processing. Again, this internal RTT is minimal within a well-architected cloud deployment. The app tier connects to the database to retrieve or persist data. Database RTT can vary significantly depending on whether the database is a managed service in the same region, a cross-region replica, or an external database. The diagram shows the response flowing back through the entire chain, with each hop adding its RTT contribution to the total response time. The important insight is that while individual internal RTT values are small, they accumulate across the request path. Optimizing cloud application performance requires minimizing both the number of network hops and the RTT of each individual hop through strategic service placement and connection pooling. RTT and DNS resolution. DNS resolution is often overlooked as a source of RTT overhead, yet it can significantly impact application performance. Before any TCP connection can be established, the client must resolve the destination host name to an IP address, and this resolution process involves its own round trips. A complete DNS resolution for a new domain can require multiple round trips. The client first queries its configured DNS resolver. If the resolver does not have the answer cached, it must query the root name servers, then the TLD servers, and finally the authoritative name servers for the domain. Each of these queries adds RTT to the resolution process. DNS caching at multiple levels mitigates this overhead for subsequent requests. The client operating system caches resolved names, the local DNS resolver caches responses, and intermediate resolvers along the path may also cache. However, cache entries expire based on the time to live value set by the authoritative server, and cache misses reintroduce the full resolution latency. For global applications, the choice of DNS resolver can impact both resolution RTT and the quality of subsequent connections. Anycast DNS services like Google Public DNS or Cloudflare's resolver provide low latency resolution from most locations, but using a geographically distant resolver might result in suboptimal CDN routing if the CDN bases its routing decisions on the resolver's location rather than the client's location. Let me explain the sequence diagram showing the DNS resolution flow. The interaction begins with the client needing to access a website at www.example.com. The client sends a DNS query to the local resolver, which is typically provided by the ISP or configured as a public DNS service. This query contains the hostname that needs to be resolved. If the local resolver does not have the answer cached, it must perform recursive resolution. The resolver sends a query to the root server asking where to find information about the COM top-level domain. The root server responds with a referral to TLD, providing the addresses of the servers responsible for the COM domain. The local resolver then queries the TLD server for information about example.com. The TLD server responds with another referral, this time pointing to the authoritative server for example.com. The local resolver queries this authoritative server, which finally returns the IP address for www.example.com. The local resolver caches this response and returns the IP address to the client. Only now can the client begin establishing a TCP connection to the actual destination server. The diagram clearly shows how a single hostname lookup can involve 4 separate round trips before the application can even begin its primary communication, making DNS optimization a critical consideration for latency-sensitive applications. RTT troubleshooting methodology. When users report slow application performance, A systematic approach to RTT troubleshooting can quickly identify the root cause. This methodology moves from simple measurements to more detailed analysis, isolating problems at each layer of the network stack. The first step is establishing a baseline by measuring RTT to the destination using ping. This gives you the fundamental network latency between the client and server. If ping shows acceptable RTT but the application feels slow, the issue is likely above the network layer, perhaps in DNS resolution, TLS handshakes, or application processing. If ping reveals high RTT, traceroute identifies where latency is being introduced. Look for hops where RTT jumps significantly, indicating problematic network segments. Compare traceroute results from multiple source locations to determine if the issue is localized or widespread. For application-specific issues, capture network traffic with tools like Wireshark to measure actual TCP or TT from SYN to SYN-ACK timing. Compare this to ICMP ping or TT to identify any discrepancies caused by different traffic treatment. Examine TCP options to verify window scaling is negotiated and functioning correctly. Let me explain the flowchart that outlines the systematic troubleshooting process. The flow begins with report of slow performance, which is the triggering event for our investigation. The first diagnostic step is measure RTT with ping to establish baseline network latency. From the ping measurement, we reach a decision point. Is RTT high? If the answer is no, meaning RTT is within acceptable ranges, we proceed to check DNS and TLS overhead. This branch investigates whether latency is being introduced by name resolution or cryptographic handshakes rather than network transit time. If RTT is high, we proceed to run traceroute to identify where in the network path the latency originates. After traceroute, we reach another decision point. Specific hop problem. If we can identify a specific hop causing the delay, we proceed to contact network provider or address routing. This might involve working with ISPs, adjusting BGP configurations, or implementing traffic engineering solutions. If no specific hop is problematic but RTT is still high across the path, the issue is likely distance or congestion. The resolution path leads to consider CDN or edge deployment, acknowledging that some latency is inherent to geographic distance and can only be addressed by moving services closer to users. Both the DNS and TLS investigation path and the network investigation paths ultimately converge on implement solution and verify, emphasizing that troubleshooting is not complete until the fix is confirmed effective through repeated measurement. Advanced RTT analysis tools. Beyond basic ping and traceroute, several advanced tools provide deeper insight into RTT behavior and network performance. Understanding these tools expands your troubleshooting and optimization capabilities. MTR, which stands for My Traceroute, combines the functionality of ping and traceroute in a single diagnostic tool. Unlike traditional traceroute, which sends a limited number of probes, MTR continuously probes each hop, building statistical profiles of RTT and packet loss over time. This continuous monitoring reveals intermittent issues that a single traceroute might miss. TCP-specific tools like SS on Linux provide insight into connection-level RTT measurements as reported by the kernel's TCP stack. These measurements reflect actual application traffic rather than synthetic probes and include smooth RTT and RTT variance values used for retransmission timing. Packet capture tools like Wireshark and TCP dump allow precise RTT measurement from actual traffic. By examining the timestamp difference between a TCP SYN and its corresponding SYN-ACK, you can measure the exact RTT experienced by the application. This method captures any differences in how routers treat ICMP versus TCP traffic. Let me walk through the command examples on the slide. The first command demonstrates MTR with the syntax MTR followed by the -R flag and then example.com. The -R flag runs MTR in report mode, which sends a fixed number of probes and then outputs summary statistics rather than running continuously. The example.com is the target destination. The second command shows how to view TCP connection statistics using SS with the flag -I for internal TCP information. The grep filter for RTT extracts lines containing round-trip time data from the output. This displays the kernel's view of RTT for established connections, showing both the smooth RTT value and the variance. The third command uses TCP dump for packet capture with the -I flag specifying ETH0 as the capture interface. The -W flag followed by capture.pcap directs output to a file for later analysis. The filter expression in quotes captures only TCP packets that have the SYN flag set, which includes both SYN and SYN-ACK packets. This capture can be analyzed in Wireshark to calculate connection establishment RTT. The fourth example shows Wireshark display filters for RTT analysis. The filter tcp.analysis.ack_RTT greater than 0.1 displays only packets where the acknowledgement RTT exceeded 100 milliseconds, helping identify problematically slow exchanges. The comment explains that this filter format works in the Wireshark graphical interface to highlight high-latency TCP acknowledgements. Combining these tools provides a comprehensive view of RTT behavior at multiple layers, from raw network latency through transport protocol performance to application-level timing. Summary and best practices. As we conclude this presentation on RTT and its implications for network performance, let us consolidate the key concepts and best practices that will help you optimize your networks and applications. RTT is a fundamental metric that directly constrains TCP throughput, application responsiveness, and user experience. The relationship between bandwidth, RTT, and effective throughput is captured in the bandwidth delay product, and optimizing network performance requires addressing both bandwidth and latency. Geographic distance imposes physical limits on minimum achievable RTT that cannot be overcome through any amount of bandwidth or optimization. For globally distributed users, placing content and services closer through CDNs, edge computing, and multi-region deployments is the only solution to geographic latency. Protocol choices significantly impact RTT efficiency. QUIC and HTTP/3 reduce handshake overhead compared to TCP plus TLS. Connection reuse through Keep Alive and connection pooling amortizes handshake costs across multiple requests. Request multiplexing through HTTP/2 and HTTP/3 reduces head-of-line blocking delays. Application architecture should minimize round-trip dependencies. Batching requests, using asynchronous patterns, prefetching anticipated data, and caching frequently accessed resources all reduce the impact of RTT on perceived performance. Let me explain the diagram that summarizes RTT best practices as a decision and action framework. The starting point is understand your RTT, emphasizing that measurement is the foundation of optimization. From understanding, we branch into two parallel investigation paths. The first path is measure and monitor, which leads to baseline and track. This represents the ongoing operational discipline of continuously measuring RTT and tracking trends over time. Without measurement, you cannot identify problems or verify improvements. The second path is analyze components, which breaks down into identify bottlenecks. This represents the diagnostic work of determining which components of RTT, whether propagation, transmission, processing, or queuing, are contributing most to total latency. Both paths converge on optimize strategically. This is where you apply the appropriate solutions based on your analysis. From optimization, three action branches emerge. Deploy edge resources addresses geographic latency by placing content closer to users. Use modern protocols addresses handshake and protocol efficiency through QUIC, HTTP/3, and TCP optimizations. Design for latency addresses application architecture to minimize round-trip dependencies. These three strategies all lead to the ultimate goal: improved performance. The diagram emphasizes that RTT optimization is not a one-time task but an ongoing cycle of measurement, analysis, optimization, and verification. Thank you for your attendance. Please consider subscribing to the channel and liking this video.